Alright, so now we're doing our video on Huffman trees, okay? So before we get into Huffman trees, or sometimes called Huffman encoding, we need to talk about what exactly encoding is, right? So encoding is the process by which we decide that some data of some kind is going to be represented as a sequence of bits. It's the process of deciding what data should be represented as what bits. Now there's two types of and basically what we're going to do is that we're going to look at specifically a form of compression, where we take some data and we move it down into a format that's as small as possible. There's two types of compression. You've got yourself lossy compression, where you've got things like videos or music, where we can throw out some of the data and it's not going to make a noticeable difference to the image quality, or we can throw out some of the higher frequencies that you're not going to hear in the music. So we can throw away some of the data that you're not going to notice and isn't that important. Or if we need to get the file smaller, then we can throw away data and you're going to notice it, but you can still get the effect of it, right? The difference between encoding something at 1080p versus 360p, right? You can still watch a video at 360p, it's just not as sharp as a 1080p video. Okay. However, stuff like text, which is what we'll be dealing with, that's lossless, which means that we do not want to throw away any of our data, right? If you're encoding something, trying to zip up a text file, right, or zip up a Word document, then you really don't. And if you sent that to your professor, they open zip it. They don't want you to be like missing half the word. So we're dealing with a kind of lossless compression here. So. One of the more fundamental things that we had to learn how to compress was, text. And we used a form of encoding called ASCII to encode everything. And ASCII is, it's kind of built in as kind of the default. Although these days it's a lie. Let's look at the ASCII table. ASCII is this table of values that says, hey, this sequence of 7 bits represents this symbol, right? Null start if we see 000, 0001, that's start of heading. If I see 001, 1010, that is substitute. If I see, if I see 011, 0010, I'm going to render that as a 2, right? So a sequence of 7 bits. And typically this was extended with one more bit for basically a bunch of other characters. Now that's a lie. Most things these days are in UTF-8 is used as the encoding, which is variable width. So things can be 8 bits or they can be 16 or 32, 16 or 24 or 32. But there's wonderful videos that have already been produced on UTF-8, which you can go and look at. But for the sake of simplicity, we're going to assume that everything is in ASCII, right? The default way that everything is encoded is in ASCII, which means that characters take up 1 byte or 8 bits, right? So that means that in the English language, if I've got something like, the entire works of William Shakespeare, right? Go to Project Gutenberg, right, to get that. Download Shakespeare. Whoops. Of course, here's his complete work. Still worked. Right, and I downloaded in plain text UTF-8, right? UTF-8, just mentioned that. It takes about 5.6 megabytes of text. It's a text file with 5.6 megabytes. It's actually quite large. There it is. So now I'm going to save it. Let's see. Desktop. Don't use the desktop that often, but here, right? Now let's assume again that this is just ASCII. It's not actually UTF-8. This character over here takes up is 8 bits. This character up here is 8 bits. This character up here is 8 bits. 8 bits, 8 bits, 8 bits, 8 bits, 8 bits, 8. and so on and so forth. Every single character here is 8 bits, right? That's the way ASCII works. Everything is 8 bits. So now, how could we possibly make it smaller? How could we possibly make this in such a way so that we could end up with a smaller document?